yours.
Right. Yeah, thanks for having me. So this is some joint work with my co-authors, Jacob, Michal, and my advisor, Sanjoy. So yeah, let's get started.
Maybe just click once with
All right.
this. Yeah.
Okay, there we go. Yeah, we're good. We're good. Okay, so k-means clustering is a super basic problem in unsupervised learning. And the broad idea is you have data and you just want to put similar data close to each other. Sometimes data naturally appears in clusters. And there's a lot of ways you can do clustering, but one of the most common ones is specifically through k-means, which is dictated by this loss function. So the way the loss function works is if you have a data set X and a set of centers S, the loss incurred by X with respect to S is obtained by summing the squared distances for each point in your data set to the nearest cluster center. And the reason it gets called k-means is if you're optimizing this loss function, it turns out the best thing you want to do is you want to split your data up into clusters that are similar to each other. And then for each of those clusters, you want to pick the mean because the mean minimizes the sum of squared distances the best. So super well-studied problem. Computing the optimal k-means clustering is actually going to be hard, but there's tons of approximation algorithms and a lot of work figuring out how to do this problem well. So today we're going to be looking at the online setting, where like in all online problems, your data arrives one point at a time for some maybe unspecified amount of time, and your goal is to kind of cluster as you go along. So there's a lot of ways of formalizing that problem as well. And for this talk, we're going to be focusing on one such formalism. And the way it works is like this. So at each time step, you're going to get a new data point, x of t, this red point. And then right away, we're going to incur a loss. And that loss is basically based on how far this point is from our current set of cluster centers, which is denoted by these black points over here. And since we're doing k-means, the loss is just going to be the distance squared. Here, distances are pretty much always assumed to be Euclidean distances, but as you'll sort of later see, all of our results will hold for any metric space. Really, most results in this field hold pretty well for, you can even go a little bit more general than metric spaces. Like you just need something that approximately obeys a triangle inequality, and the results will usually work. But anyways, the point is, so each time step, we get a loss like this. And then after we incur the loss, we're given a chance to update our cluster centers. So over here, maybe because we saw that red point over there, we would want to move one cluster center from there to there, maybe to be more representative. And then this just keeps repeating. So you get another point, you pay your loss, and then you update your centers. And the idea is you want your loss to be as small as possible. And hopefully over time, as you're moving your centers around, you will find centers that represent the data pretty well. So in this problem, we sort of have three goals together. So the first goal should be that our loss is small. And typically in all sorts of k-means clustering problems, you measure your loss relative to the best set of k-centers. And then the second thing we want is the number of cluster centers we have should be small. Now, in a lot of settings, you would assume this is exactly k, because in k-means clustering, you're comparing to a set of k-centers. But for this problem and many other settings, you typically relax this to allow yourself to use more than k-centers. Sometimes you use like O of k, sometimes you might use like O of k log n, but the idea is you want it to be related to k and small. And finally, this third goal is we want the algorithm to be quick and efficient. There's a lot of algorithms here that are theoretical that do well on the first two things, but not so well on the third. And for this particular setting, previous work was due to Cohen-Addad in AI stats, I think in 2021, where they achieved pretty good results for the first two criteria. So the first one says that their loss, so you notice here the loss is the distance from each point xt to the set of cluster centers at the previous time step. That comes because your loss is assigned before you adjust your centers. And they showed that you can get arbitrary close to the optimal loss. The number of centers they output is exactly k, but their algorithm was exponential in time and space. So the idea of their algorithm was sort of based on using like a expert space clustering, where they sort of had one expert correspond to pretty much every set of k possible points. And they had some clever way of like maintaining weights on these experts. But the point is partitioning space into sets of k points results in exponential memory and time. So in this work, we're trying to improve on this, specifically improve on part 3. So what we do here is we relax the first 2 conditions. So instead of getting within a 1 plus epsilon factor, I just want to be within a constant factor of the best possible loss.
Just a quick question. So
Sure.
this best possible loss, it assumes that the centers are fixed. Because
Yes.
on the left-hand side, the centers change, but on the right, the centers don't change it.
That's right, that's right. So you can think of the best possible loss as someone who doesn't have flexibility in choosing their centers, but they have foresight. They know what the entire data set's going to be. So they choose the best set of K fixed centers that works well for everything.
Would it be a significant change if you, on the right, you also allow the centers to, say, you fix K, but you allow the centers to change?
Right, so.
If n is big compared to K, would it affect the right-hand side?
So you're saying we allow the centers, instead of picking K-fixed centers, we compare ourselves against like some sort of adaptive optimal?
Yeah, if you compare it to some kind of adaptive optimal.
Right, so you would have to constrain your adaptive person really well, because this guy you're comparing to is going to be typically something with some sort of foresight as to how your sequence works. And if you knew what your sequence would be, you could achieve 0 loss by just knowing what the next point is. Then if I can change my centers, I would just predict what the next point would be and move one of my centers there. So you have to have some sort of limitation on what we're comparing to.
Right. Well, yeah, I guess I'm just assuming that extent comes from some distribution, but it's not necessarily the case.
Right, that's
here.
right. Yeah. So we're very much in a lot of clustering problems in online clustering. We assume literally just any arbitrary sequence. It can even be adversarially chosen, not to the point of, a sequence that watches your algorithm work and in real time chooses things. That's too adversarial, but we assume we make no assumptions on the data sequence. I think it is an interesting direction though, to assume your points are sampled from some sort of data distribution or something like that, for sure. So yeah, so that's what I mean. We're comparing to the best set of K centers, and we just want to be within a constant factor. And for the number of centers we're allowed to output, we're going to also relax that. So instead of being exactly K, we'll allow ourselves to differ by like a polylogarithmic factor. This is maybe not super desirable because, log n it does go to infinity as n goes to infinity. But reducing this to K would be definitely a direction I'm interested in for future work. But finally, we really want the algorithm to be quick. So we're going to require K polylog n runtime and memory. And the reason you want the memory to be log n as opposed to n is if you allow yourself O of n memory, you could essentially memorize all of your points, which doesn't feel online anymore, kind of feels like cheating. So we want to look at algorithms that really improve on that. So kind of right away, you'll realize in this formalism that you get stuck on a very adversarial looking sequence. So imagine a sequence of data points where it's initially kind of close together, but then you just get points that are super, super far away. Like for example, in 1 dimension, you could just pick like a crazy exponentially increasing sequence, or in 2 dimensions, I kind of tried to draw a picture. And the point is, it seems like no matter what you do on this sequence in online clustering, you have no chance of success. Because presumably, if I see a bunch of points in a small area, I'm going to pick clusters in that area. And I really have no way of guessing where some super far away point will come from. So you can actually show that on such a sequence, pretty much no matter what my algorithm is, I'm forced to pay these really, really large losses on every time step. And there's really no way of getting around this. So there's sort of a natural lower bound quantity that bounds how well you can do in this problem. And that looks like this. So over here, I'm saying that basically, an informal version of our theorem is any learner is going to incur a loss that's at least this quantity on the right. So I call this quantity on the right, we call it lambda xn, and it's basically the sum of the distances for each new point to its nearest neighbor from all data points that came before them. And you can think of this loss, so kind of like our previous loss that we're looking at, like the optimal loss was sort of the best set of K centers, like that. You can think of that as the learner that knows your entire data sequence. This learner is a different kind of learner, this lower bound term, and it's a learner that basically memorizes the entire data set. So imagine if I just memorize my entire data set and output in my entire data set as cluster centers, the loss I would get would be lambda xn. And really this theorem is not all that difficult to prove, because all I'm saying is you can't do better than just memorizing your entire data set. And so when you keep that in mind, what we can do is we can adjust our goal. So our goal originally was to be within the constant factor of the best K centers in hindsight. Now we're going to introduce a term of lambda, which is the thing that memorizes the entire data set. So this is our updated goal. We still want to have K log n centers, and we still want an efficient algorithm. So when you make this adjustment, there's actually a very natural starting point to try to build an algorithm for this setting, which is to build on this huge literature of other online clustering algorithms. So this setting I'm looking at is kind of special because of the fact that you pay loss before you get to adjust your centers. There's tons of other settings that are differently structured. And one of them is called the streaming setting. So you can see in the streaming setting, the loss function looks very similar to ours. So ours is the online setting where you can see you get charged a distance from x sub t to s sub t minus 1, s sub t minus 1 being your set of centers at time t minus 1. And in the streaming setting, you just like look at fix some time n, and it's typically really large. And at time n, you take the whole clustering loss of your entire data set with respect to your centers at time n and measure it to the best possible thing. So the inspiration for the streaming setting is rather different. It's sort of like, imagine if you had a super large data set and you wanted to cluster it efficiently without like storing your entire data set in memory. You sort of read your data set one point at a time, adjust your cluster centers, and you just want to end up with a good clustering. The streaming setting has been super studied. You don't even need to know exactly what n is in advance, but there's many ideas that work really well for streaming. And for the online setting, the only real previous work was the one I discussed earlier from AI Stats. Streaming, on the other hand, there's like a lot of work. People have gotten really, really good at this problem. So really natural question is, what if we just took one of those streaming algorithms and applied it to the online setting with the hopes that, in the online setting, our goal is a little bit less ambitious because we have this lambda term that we want to be within. So perhaps a streaming algorithm would work well. And I don't actually have a definitive answer. It's possible that, one of these like 200 algorithms would do well in the online setting. But what I do know is there's no like direct reduction. Like there exist streaming algorithms that are not going to do well in the online setting. And so to see that, just consider like a very simple toy example. So let's say your data set is basically this set of points that live on a circle. I guess you could parameterize it like cosine theta, I sine theta. And the way the data set works is x just cyclically moves throughout this thing. I realize now that I did the unit circle backwards, but it doesn't really matter. And imagine a clustering algorithm where at each time step, it just takes the previous k points that you've seen so far. So the idea is this, so every time step, the red point is a new point and the blue points are the previous clustering. So at all times, the set of blue points is actually a really, really good clustering for my entire data set. And the reason is because my data set only has k plus 1 total locations. I guess over here I picked 8. So k is 7. And I have 8 distinct areas my data comes from. So picking any seven of them and sitting on them would be a great offline clustering. So in a streaming sense, this output does really well because no matter where you stop the stream, you're going to have k distinct centers that have a good performance. However, in the online sense, because you keep shifting the set of centers you get, every time we pay this loss. The loss we pay is the distance from the red point to the nearest blue point. So the total loss we're going to incur is going to be like the distance between these points times n. That would be the online loss. While the offline loss, like the streaming loss, would just be the loss of all of your data versus 7 of these points fixed at a given time. And that's actually going to be a lot smaller. And the amount it's smaller is a factor of k. This is not too hard to show, but basically if you freeze at time n and you just compute the loss, the k-means loss of your entire data set with respect to the set of blue points you had at time n, you would find that you're within a constant factor of the optimal. In fact, you literally are the optimal because I guess the optimal would take a mean of 2 points or something like that, but you're very close to the optimal. But meanwhile, in the online case, since we paid a distance every single time, you're off by a factor of k. And when k is large, this is not within our parameters of being an O of 1 approximation. So directly streaming doesn't work too well, is at least the intuition I got from playing with this. So there's a simple idea, which is kind of the trouble with that example was I kept shifting the set of cluster centers that I had. So maybe imagine an algorithm that doesn't shift cluster centers much. Like once it picks a center somewhere, just hold on to that center and maybe you add additional ones. Yeah, go ahead.
Can you go back?
Yeah, sure.
So you, in your modified goal, you added the second part. Which
Oh, that lambda part?
this error coming from the second part in this case?
A good question. So this example was also constructed so that lambda is very, very small.
Okay.
And the reason is lambda is what you get, is the error you would incur, right? If you memorize all your data. After you see the first k+1 points of this data stream, you've seen every possible iteration. So you would cease incurring loss. Yeah, I should have mentioned that. That was a good catch. So take an extreme idea in which we never delete centers. That kind of prevents me from that annoying case where I adjust my centers and sort of like the data appears right where I deleted my data from. And what we can show is actually when you do this, the behavior you get in the online setting is pretty nice. So this is kind of a key lemma in our paper, or a variant of a key lemma in our paper, which is you show that if you have a learner that does satisfy this constraint, the loss it incurs is bounded by lambda, which is that lower bound term that I said was inevitable, but also this other loss term over here, which looks very similar to our loss term, but there's like a key difference. And the key difference is xt st minus 1, that's the online thing where you look at your previous set of centers. Now you measure with respect to your current set of centers. So for examl, sum of dxt comma st would literally be 0 if I always pick each new center as a cluster center. The caveat, of course, is in this setting, we can't remove centers. So, if you just pick every single point, you're going to get way too many centers. But the point here is this lemma is really nice because this loss term, I can study using all of this established literature in the streaming setting. And that's going to be one of the key ideas of our paper. So I actually want to go into how we prove this lemma because it's actually not very hard at all. So kind of the idea here is, are there any questions about this lemma or anything else so far before I go on to the proof? No? Okay, cool. So to prove this, our goal basically is to show that this online loss is bounded by these two terms over here. So what we're going to do is basically appeal to the triangle inequality. So we're taking any term in that sum. We have the distance from xt to s sub t minus 1. And what we do is we first pick the nearest neighbor of x sub t among data points that appeared before it. This is obviously inspired by this lambda term where we look at our nearest neighbor in previously streamed data. And then for that point, we look at its distance to s sub p sub t. This is just to get the loss term, the desired loss term that we want. And the final thing is to notice that s sub p sub t is a strict subset of st minus 1 because we never delete points. So if we just apply the triangle inequality, we can sum these the three left quantities to bound the right quantity. And you end up with an inequality like this. I'm being a little bit willy-nilly with constants, like when you have distance squared, you actually have to include a factor of 2 or something when you do the triangle inequality, but that doesn't really matter because, I'm using big O notation to hide all constants. So basically taking a sum, we can bound our loss as follows. And over here, maybe this thing will go away, but it's blocking, what is it blocking?
Maybe if you click it on the screen.
Oh, that's so interesting. It does not appear on my computer.
Okay.
Well, okay, this thing over here says desired loss.
Yeah.
So this term on the right hand is the loss we want, that dxtst, and the thing on the left hand part is exactly the lambda term.
Quick question.
Yes.
What is PT?
PT is the nearest neighbor of xt. So xt, you can define PT to be like the index I such that xi is the nearest neighbor of x sub t among data that came before it. I used p, I guess, because it's kind of like parent, but maybe I should have used n, but n was already used for other stuff, so that's where it came from. So if you're sharp, you'll probably notice that I am hand waving something, which is this is not going to be our desired loss if p is not injective. Right? Because this thing is going to sum over all points t, but p of t, you might have the same nearest neighbor a bunch of times, in which case it's something random. So this is sort of the problematic case. Imagine you have a bunch of points that all map to the same point x of pt. So what you can do to get rid of this issue is you can kind of just use the triangle inequality again. So instead of using p, we'll make a new map p prime, where for the earliest point, we'll still map it to the nearest neighbor. And for everybody else, we'll map it to the guy that came before it. And what this ends up doing is you can really use the triangle inequality on all those little triangles you end up seeing. And you'll see that the distances for P prime are bounded by the distance for P by, I think, a factor of 2. I mean, it depends again with your using square distances, but it's not a big factor. And so if you repeat the same argument I gave on the previous slide with P prime, you do end up getting this lemma.
Will you replace, yeah, you replace PT by, you said, the guy that came before, in which
Right.
sense?
Yeah. So over here, I guess in the previous slide, we have this map. We have this whole little diagram with X and P sub T, right? So instead of P, use P prime.
Mhm.
And the way P prime is defined as, so take each point, you map it to its nearest neighbor. Or I guess you map it to the latest point that came before it that has the same nearest neighbor.
Okay.
That's what it would be.
Is
Okay.
that what PTs?
That's what P prime would be.
Uh,
P is nearest neighbor. P prime is built on top of nearest neighbor like this. So for X sub T1, so let's say X sub T1, X sub T2, they all appeared in that order. And X sub T1 has nearest neighbor, XPT. So all of these by P are mapped to the same nearest neighbor. I would construct this new map P prime by taking the first one, sending it to the nearest neighbor. But then the second one that also gets mapped to the same nearest neighbor, I would map it to the first one, and so on and so forth. And this map is basically designed to be injective, because anytime two things get mapped to the same thing by P, they will no longer get mapped by this construction. Cool. So yeah, so this idea turns out to be helpful for building a good algorithm, but we still get stuck. And the reason we're still stuck is that you can still have these pathological examples where your data is super spread out. This is sort of the same example I showed you guys earlier. And the issue you get on these examples is that your data, if we're trying not to delete points, then we're going to end up wanting to select lots of points. Because like when you have points that get super far away, if you have any kind of reasonable clustering algorithm, they're going to be like, this is a really important point. It's not like anything we've seen before, so we should probably select it. Now, because we're trying to hoard things and we're not trying to delete points, you're going to hold on to a lot of data from the past, and it's sort of like you're going to hold on to every point that's sort of really far away from points that came before it. This is not a problem in terms of your loss function. This is a problem with your other goal, which is you don't want to select too many centers. So kind of what this means is we are going to need to delete points after all. While our whole lemma was built on the premise of never deleting centers, turns out deleting centers is helpful. But what we want to do is we want to delete them in a smart way so that kind of we can still leverage the properties of that lemma that we just proved. And so our second idea for doing that is tracking the scale using online k-centers. So k-means is what I've been talking about this whole time. K-centers is sort of a related clustering idea that turns out to be much simpler. So the k-centers loss function works like this. If you have a data set and a set of centers, the k-centers loss function is simply for each, yeah, I guess it's just for the entire data set. So it's just for your entire data set, you take the point that's furthest away from one of your centers, and that distance is exactly your loss. So in k-means for each cluster, while we care about sort of like, you know, what is your total sum squared distance to all the points, in k-centers, we just care like literally about like the diameter of the set. And it's not like immediately clear why this is easier, but it is easier. There exists really simple, there's an algorithm by Charkar from 1997 that just maintains an 8 approximation to k-centers. It's like 5 lines long. It uses literally k memory. You only need to store the k previous centers, I think, and super simple. It's also deterministic, which is also nice. So, and it kind of makes sense because it's sort of like in k-centers, if you have something that's super far away from everything else, you can just not care about anything that's like closer together. So k-centers turns out to be a good tool for us to approximate scale. And the reason we're gonna, you know, we could have defined scale a number of ways. The reason we're gonna pay attention to k-centers is it gives you a very loose bound on the best possible k-means loss, like this. So I use W to denote the k-centers loss, and L sub mean, that's the k-means loss that we've been talking about the whole time. And so there's a really, really simple lemma which says that your k-centers loss is, it basically, if you square it, it bounds your k-means loss up to a factor of t. And the reason for that is it's not a fancy argument. It's almost trivial. It's just that if you have a k-centers loss of w, your k-means loss can be upper bounded by just taking w squared and summing it for every single point, because it's basically the loss you get if you use the k-centers as your k-means. And for a lower bound, if your k-centers loss is large, that means like by the pigeonhole principle, some two things that get assigned to the same k-means cluster are going to have a distance of w between them. I guess a distance of w over 2 between them. And this means your k-means loss is w squared over 4. Actually, I think that should be w squared over 2, because now that I think about it, you have 2 of them, but it doesn't really matter. So the point is, with k-centers, I have an approximate guess at what my k-means cost is. Now, approximate is off by a huge amount. T can be really, really large, but we'll see that turns out we have a way of dealing with it when it's just T. So with this idea added in, we're now ready to give our algorithm. So the way our algorithm works is we keep track of these things we call scale changes. And scale changes are just instances where the k-centers loss increases by a lot. The idea being, if the k-centers loss increased a lot, that means that we probably should now be deleting points, because old centers that we had are not going to matter as much. So the amount that we care about turns out to be about related to square root of t, and that just comes from the fact, on the previous slide, you remember that the w was squared when I compared it to the k-means loss. And so every time I detect that wt is larger by a factor of 16 square root t than my previously marked k-centers cost, what I'll do is I'll do a reset. So I will set my new wt to be, my new w old to be wt, my new t old to be t. And then the important thing is I will delete every center I've ever selected in my process before the time t sub old. I'll just replace it with the k-centers clustering of that time. So basically I'm deleting all my old points and replacing it with a very, very coarse summary. Now remember in the previous slide that we knew that the k-centers very loosely bounds the approximate k-means cost. But because this is all from an old time scale where the w is so much smaller, it doesn't matter that I'm off by a factor of t, because compared to the current cost that I'm paying, it'll be trivial. And so that lets me replace all my centers from before. And then I kind of just reset my algorithm. I'll explain what R and F are used for in a second. So the algorithm, which is based on a simple algorithm by Liberty from 2016, this is what I mean when I say we can borrow ideas from the streaming setting, is you basically just randomly pick points to be part of your cluster centers. And the way you do it is you look at how far away it is from your current set of centers. And if it's really far away, you should be more likely to pick it. If it's close by, less likely to pick it. That just makes sense. Things that are very far away are more likely to be meaningful. And you have to normalize by a factor of R, and R is kind of the critical normalizing factor. And if you select a point, then you increment F, which is a counter of how many points you've selected. And if F gets too large, that's indicative that your value of R is too small because you're selecting too many centers. So what you do is you just double R and reset F. And that's it for the algorithm. And the intuition here is that this doubling and resetting procedure that you do will push you to an equilibrium where you're not likely to select more than like k log t points. And once you're in that equilibrium, that's going to both help you bound how many centers you end up choosing, and also help your value of R be appropriately selected. So it turns out that if R converges towards the literal optimal k-means loss, that's like the best regime. That's where you're not likely to select too many points. And it's also where your cost, your online cost, can be efficiently bounded. And basically our strategy for getting there to that regime is we just keep doubling R until it's around that regime. And doubling alone would be too slow for data that increases with erratic scales. That's where our second step earlier comes in, which is where we track the scale. And by tracking the scale, we sort of ensure that cases in which like the optimal k-means loss grows by a lot are going to correspond to one of these scale changes. So these two ideas are sort of the two ideas I outlined earlier. The first idea being don't delete centers. You'll notice algorithm 3 has no mention of deleting centers, like step 3. And step 2 is where we track the scale. So kind of before I go into why our algorithm works well, one of the first things I want to do is reassure you that our lemma is actually not damaged, even though we're now deleting centers. And kind of this was the critical diagram for our lemma, where we took x sub t and okay, I renamed it to s for some reason, but this was supposed to be x sub p sub t. And in this triangle inequality, the only thing that changes is the distance from s sub s to s sub t minus 1 is not 0 anymore, because we might be deleting points now. This just gets replaced by W old, which is the old k-centers cost. And that's because whenever I remove points, I only remove them when I maintain a k-centers summary. So it turns out when you include these W sub olds inside the old bounds that I was doing before, by the properties of sort of kind of literally by the lemmas and equations I wrote earlier in the slides, you can just bound the total loss. And I think all that happens is your constant factors increase a little bit. So using that idea, our algorithm achieves the following performance. So the total cost incurred at any time is O of the best possible cost with k-centers plus that lambda term. And the number of centers that we output at each time is small. So it matches, it's kpoly log n. And finally, you can just see by our algorithm pseudocode that clearly if we don't select too many centers, the running time is going to be very fast, because the only data that we hold on to aside from the centers is the value of R, the value of F, W, and I guess you need to keep a little bit of information. So in that step above where we replace the centers with k-centers clustering, you're going to need to store these k points, but k-centers is very easy to efficiently do with low memory. So our total memory is also k log n, which means that our time is k log to the something n. Yeah, we're here. So that's how our algorithm does. And the proof idea is, I kind of give a very, very basic sketch here. But the first main step is what I've mostly been talking about, which is the lemma that lets us reduce the online cost to this streaming cost. Then the idea behind how to analyze this algorithm, this is the idea given in Liberty's paper that we've sort of extended to work in our setting, is you take your data and then you partition it into cluster rings. So what I mean by take your data is, we're trying to show that the cost of our algorithm is close to the optimal k-means cost. So I was saying, like, let's consider in this case the 3 optimal centers, optimal clusters rather. And then what you do is you divide them into these rings where each ring is approximately evenly spaced from the center of the cluster. And the idea is going to be that for any of these rings, if you just take one of these rings and run our algorithm on it, assuming the value of R is appropriately selected, the cost you incur on that ring is going to be very small. And the reason for that is if you pick any point on the ring, that point on the ring is a pretty reasonable cluster center for that entire ring. This also explains why we end up with all of this k log n terms running around, because the number of rings you get is about k log n. You have log n rings per cluster center and you have k clusters. And right, so the magic value for R, as I alluded to earlier, is approximately your optimal k-means cost. And I think that, yeah, so what you can show is that these ring structures is what lets you get there. If R is too small, it's naturally going to double a bunch of times. And R, provably, you can show with high probability, R never gets too large. So there's a lot of technical details in this proof in managing how you ensure that the value of R is not actually independent from the selections you make. They both change together. But once you handle those details, it's not that complicated. This idea basically works out for the proof of the approximation factor. And that basically gives us these results here. So, you know, I think 1 and 2 are not very, they're decent, but they're not very good compared to previous work in the setting. But it's really 3 where our algorithm makes improvements. It's something you could actually code, for example. Not that anyone has. So There's a few future directions I'm sort of interested in thinking about this problem. I think kind of the most obvious one is, can you do better for approximation factor and center complexity? So I think right now an algorithm's weakness is it selects a lot of centers, like it's kind of like k log to the 5 or 4n, something like that, plus constant factors. So I think that, well, that's our bound on it. I imagine if you ran it in practice, you'd find it selects less centers than you would think. But I think having something that's bounded by k would be pretty interesting. Second direction is something that's sort of a flaw in a lot of k-means clustering, which is we kind of specify the value of k ahead of time. Like we say, oh, we want to be within a close to the optimal 10 means clustering or something like that. I think something that adaptively figures out the right k could be very interesting. And sort of we're limited in this setting because we assume our data is arbitrary. And if we had more structure to our data, sort of as like Stas was mentioning earlier, maybe there's like natural values of k that work better. And finally, our algorithm, kind of as shown by the structure of the algorithm, every time we have like a large change in the scale, it kind of increases the value of r, right? So our r sort of normalizes how many points we select. So it makes us a lot more likely to, we sort of get stuck in this regime where we only have a really large scale and we stop caring about small scale differences between points. And a weakness of this is you could have a data stream where maybe like there's a transitional period where the data stream comes from one region of space and then it shifts to another space. So our algorithm is going to immediately get very like stuck being like, oh, I need to maintain clustering in both the first regime and the second regime. And it's going to stop caring about details within the regimes. But maybe in the future, all we care about is, details of running around the second regime. So I think that having some sort of idea of like, I thought forgiveness was the word I used, sort of like you forgive the algorithm for caring about these huge jumps in your data. And if you sort of forget about them, maybe there's ways of having algorithms with different guarantees. So problem number 3 would require a different problem setting. Problems 1 and 2, I think, fit within this problem setting, with problem 2 just changing whether the value of k is known ahead of time or not. So this is actually all I had prepared. I think I went through this a little faster than I anticipated, but I'd be happy to take any questions. And also we can end early. But thanks, guys.